Okay, here's our notes for today. They are on related rates. And before we get into a problem with related rates, I first want to go over when you're taking derivatives, you don't always have to take dy dx. Okay, we can take derivatives with lots of different variables. So, for example, if we want to take the derivative of a formula, we can take the derivative of a formula and we might not have an x or a y in it at all. So, for example, if I have the formula for area of a circle, so if I have area is equal to pi r squared, I can figure out how fast is the area changing in relationship to the radius by taking the derivative of this. So the derivative, I would write dA dr. Okay, so normally we would have y equals pi x squared, and we would say dy dx. Well, now we're finding the derivative of a in regards to r, so we write dA dr. And if we take the derivative of that using our power rule, bring the 2 down in front, we would get 2 pi as a constant, and then minus 1 from our exponent, so we get 2 pi r. Might want to notice that's also the formula for the circumference. Very interesting. Okay, so what does this mean? What is the meaning of the derivative? This is the change in area per unit of radius. The change in area, okay, this is the change in area per unit change in radius. So if the radius, say, changes by 1 centimeter, the area is going to change by 2 pi centimeters, because if it's changing 1 times 2 times pi is 2 pi. If the radius were changed 3 centimeters, then it would be 6 pi would be the change in the area. Okay, so this is the change in area per unit change in radius. Kind of like when we take position and we change it to change of an object, we're talking about speed. So that one we're going to do next. Okay, so for my next formula, what if I have the formula for position of an object dropped from a height? So the position of an object is equal to negative 4.9 t is time squared plus this number that I'm going to put here is the starting height. So let's say we have an object starting at a height of 20 meters. Okay, why negative 4.9? Because that's half of the acceleration of gravity. And that's what we use in the formula for determining the position of an object that is being affected by gravity. Okay, so this equation is for the position of an object dropped from a height of 20 meters. Okay, so that's this formula right here. So if I take the derivative of this, so the derivative would be the change in p over the change in t. If I take the derivative, well, just using my power rule, 2 times negative 4.9 is negative 9.8, and t, and the derivative of 20 is just 0, so that just goes away. So there is my derivative of my position. So what is this? The meaning of this is it's the change in position over time. Change in position, well, that's like distance, how far it's gone. How far has it gone over time? So this is just speed. This ends up being the speed of the object, okay, such as meters per second. So this is the speed of the object. Okay, because this would be, position is measured in meters, so this would be like meters per, the unit of time is going to be seconds. And I know it's going to be seconds because this formula uses acceleration of gravity, which is 9.8 meters per second squared, meters per second. Okay, so we're operating in meters and seconds here. Okay, well, what if I wanted to take the second derivative of this? If I take the second derivative, that would be d squared p over dt squared, second derivative, and the derivative of this would just be negative 9.8, and that is the acceleration. That is the acceleration of the object, which happens to be the acceleration of gravity, negative 9.8 meters per second squared. Okay, so the units on this would be meters per second squared. Per second squared. Okay, so we can take derivatives of any formula and try and make meaning of them. Okay, we can make meaning of these as well. All right, next thing I want to say, sometimes in order to solve a problem, we might not be able to take the derivative and get the rate that we want. So we need to take a couple of formulas and take the derivatives of both formulas and work them together to get the outcome that we actually want. So we had this in our business calculus problems where I told you we had a related rate problem that we wanted to figure out. So, but we can do this with all kinds of different situations. Okay, so let's go ahead and write that down. What are we going to be doing now? So sometimes we want to know the rate of something changing, but we don't have the formula directly relating the two quantities. Okay, so if we need to find the rate of something changing in regards to something else, but we don't have a formula that directly relates those two quantities, what we can do is we can take two formulas, one that has one of the quantities that we're interested in and another formula that has the other quantity we're interested in, and we can use the chain rule to put these together. Okay, so we can use the chain rule to put two different equations together. So as we saw in the business calculus problems that we were doing, it actually just looks like multiplying and dividing fractions. So we're going to put the formulas into our notes, just like we had them in the business calculus problems. So I'm going to turn the page so I can write down my formulas, and then we're going to do an example. Okay, so I really don't need this whole page, but I went ahead and set up my example on the next page already. So you could certainly put your example on the same page that I'm now putting the formulas. So the formulas, and you could be using any letters. The idea I'm just giving you is that you can see how things cancel out. So dy dt, so say I wanted the change of y in regards to the change of t, but I don't have a formula that is putting together y and t. What I can do is I can get a formula for the change in x in regards to t, and times it by the derivative for the change in y in regards to x. And that's what we usually have, right? We usually have an equation y equals something with x, a function of x. And if I put these together, notice dx over dx just reduces out. Dx divided by dx is just 1. So we can treat these derivatives just like we would treat multiplication of fractions. We can reduce out the dx over dx, and we're left with dy over dt. So if I have two formulas, one that relates x to time and another one that relates y to x, I can then multiply them together and be left with the change in y in regards to t. Okay, or if I don't have dy dx, let's say I have dx dy, I can use division. Okay, so dy dt. Okay, likewise, I could do dx dt divided by dx dy. Okay, so in case I had my formula said said x equals, and then I had something going on with y, I could take the derivative of that and then just use division. Because when we change this to multiplication, when we divide fractions, right, we change it to multiplying by the reciprocal, which would be this. Okay, so this is what we're going to be working on with our example and with your math space assignment after the notes. Okay, so that probably could have not been on a page by itself, but I thought I was going to take up more space on the previous page. So here is our example. The volume of a cube is increasing at a rate of 2 meters cubed per second. Find the rate of increase of its surface area when the cube has a volume of 27 meters cubed. Okay, so we got a bunch of information here. So first we should go through and figure out what formulas do we need, because it doesn't give us any equations here, right? So it does give us volume, and it does give us surface area, and it mentions volume again. So it looks like we probably need these formulas. So if you don't know them, then check your formula packet. They should all be in your formula packet under prior knowledge. Let's see if I have the formula packet here. Yes, I do. So if I look at my formula packet, actually, these are so easy, they might not even be in here. Yeah, they have a cuboid, which is length times width times height, but a cube, the length, the width, and the height are all the same. Okay, and then surface area, do they have any surface areas in here? Doesn't look like they do, but surface area of the cube is easy enough. Well, that's kind of funny. I thought they might have more of those formulas in here, but it doesn't look like it. Okay, but that's all right. We can figure this out. So volume of a cube. Let me get my notes so that I don't mess up. If we have a cube, let's just go ahead and make sure we all know what we're talking about. Cube. Okay, there's my cube. All three dimensions are going to be the same, and I'm going to go ahead and call those S. So the side, okay? All three of them are the same, so my volume is equal to S cubed, okay? S cubed is going to be my volume. Okay, the surface area of this, and I'm just going to use the letter A for surface area because I don't like using SA because that's going to get messy when I start doing my derivatives. The surface area is, well, each surface is a square, and there's 6 surfaces, so it's going to be 6 times the side squared because it's the area of each side, and there's 6 of those sides. Okay, so there's my formula for volume, there's my formula for surface area. Now it's saying that I know that the volume is changing at a rate of 2 meters cubed per second. Okay, I'm going to reserve that information for a little bit later. What am I trying to find? Find the rate of increase of its surface area. So the rate of increase of its surface area when the cube has a volume of 27. So the rate of change of the surface area, that is going to be dA, the derivative of A, the change in A in regards to time. Okay, when it says the rate of increase, since it's not giving us another quantity, the rate of change of the surface area in regards to something else, then we can assume it's in regards to time. Okay, because notice here we have a rate that in regards to time, meters cubed per second. Okay, so I'm trying to find, what do I need to find? I need to find I need to find, and I didn't leave myself enough room for this, I need to find dA, change in surface area, in regards to time, the rate of increase of the surface area, dA dt. Okay, so right here I don't have any t's, but let's go ahead and see what I do have. Let's go ahead and take the derivatives of both of these and see what that looks like. So if I take the derivative of the volume, I'm going to get dV ds, because it's in regards to s. Okay, it's in terms of s. So I'm going to get 3s squared. And then if I take my derivative of the area, I'm going to have the change in area in regards to s. I'm going to have 2 times 6 is 12. I'm going to have 12s. Okay, so the change in volume in regards to the side length is 3s squared, and the change in area in regards to the side length is 12s. Okay, that doesn't help me find dA dt yet, so I need something with time, and that's where I come back to this one up here. This one right here, it says the volume of the cube is increasing at a rate of 2 meters cubed per second. The volume is changing, it's increasing. The volume is increasing. We can think of that as changing at a rate of 2 meters cubed per second. So that piece of information, this piece of information right here, I can write as the change of the volume, the change in the volume in regards to time. Because see, this is volume over time. This is volume and this is time. So the change in the volume in regards to time is equal to 2. Now I'm in luck now. Now I have that variable in terms of time. I've got a time, which is what I need to find my change in surface area in regards to time. So now I'm looking good. So now I just need to figure out, how do I put these 3 things together in order to end up with this? So I noticed that I want to have a dA, so I'm going to start with my dA first. So I'm going to go ahead, and I got new pens. I bought them for myself over the holidays, so I got to use all my colors. Okay, so I'm going to go ahead. Oops, what happened there? All right, so I'm going to start with this one, dA ds, and I want the s to go away. I don't want the s. See, this is what I'm trying to find. I'm trying to find dA dt, so I want the s to go away. This one has an s, so to make it go away, I need to multiply by the reciprocal of this. Or, in other words, I need to divide by dV ds. Because if I multiply by the reciprocal, the ds's are going to go away, and I'm going to be left with dA dV. Okay? Okay, something else I can do. If I have my dA dV, once I have dA dV, I can then multiply by dV dt, which I have right here, dV dt. And notice the dV's are going to cancel out, and what am I going to be left with? I'm going to be left with dA over dt. And that's what I'm trying to find. I'm trying to find the rate of increase of the surface area. So that's in regards to time. Okay, so now let's go ahead and plug in what I got. So dA ds is 12s. Look at all my beautiful colors. So this one is 12s. I'm going to divide that by dV ds. dV ds is 3s squared. Okay, so let's go ahead and we'll simplify that. So that is the same as 12s over 3s squared, which simplifies to 12 divided by 3 is 4, and s over s squared is just s. So there's my dA dV. So my dA dV is 4 over s. So I'm going to take my 4 over s, that's my dV dA. I'm going to put a semicolon here. So now we're going to do this one. So dA dV is 4 over s. okay, and that's an S, not a 5, times dv dt. dv dt is 2. So I'm going to multiply this by 2, and I end up with 8 over S. So I now have an expression for dA dt. So I know that dA dt is equal to 8 divided by S. Okay, so the change in area in regards to time is going to be 8 over the side length, and that's going to be meters squared per second, because area is meters squared and t is seconds. Okay, so I need to finish this up though. I need to actually find a value, and it tells me when I want to evaluate this. I want to evaluate this when the volume is 27. When the volume is 27 is when I want to know what's the rate of the change of the surface area. So it gives me volume, but I need S. But fortunately, we have a formula for that. Volume equals S cubed. Okay, so I know that my volume is equal to 27, and I know that that's equal to S cubed. So to solve for S is going to be equal to the cubed root of 27. So that means S is equal to 3. And so now I can substitute in my 3. Oops, running off the bottom of the page. I can substitute in my 3 for my S. And so I get my final answer. The change of the surface area, the rate of change of the surface area when the side length is 3 or the volume is 27 is equal to 8/3 meters squared per second. Okay, so the big takeaway on this is that if you have derivatives, when you're taking derivatives, instead of like writing v prime or a prime, write it in terms of, write the derivative using the letters that are in the formula. So then that way you can take all your different derivatives and figure out how to multiply them or divide them with each other in order to be left with the rate of change that you are looking for. Okay, so you are going to do a math space assignment with a whole bunch of problems just like this. So remember, you can look up formulas. If you don't know the formula, say for volume of a cube, go ahead and you can look it up on the internet at this point. Okay, if they don't give it to you in math space, whatever formulas you need, you can just look them up. All right, good luck. That's it.